Hey guys, what we're going to cover in this video is PCA and EFA, specifically EFA, with a small comparison to principal components analysis. So both principal components analysis and exploratory factor analysis are descriptive analyses that you use to understand an underlying pattern in the data. They generally group variables together based on high correlations between patterns of answers. So mostly this is a data reduction technique. PCA stands for Principal Components Analysis, where you make components, and they're combinations of correlated variables, and the variables are thought to cause the components. So that's a key feature here, is that variables are thought to cause the components. Put a star there. I like to ask this question on quizzes. You produce components, which is the term that you'll use when you're writing, and the variables, when you're looking at the variance in the data set, all of the variance is used, so the total variance. That's another key difference between PCA and EFA. Exploratory factor analysis describes the data and summarizes factors. And in the reverse, factors are thought to cause the variables. And that is where an underlying construct is what creates the scores. So generally, this is the way psychologists think about phenomenon. So IQ, my IQ causes the answers that you see on a standardized IQ test, not that my answers on the IQ test create my IQ. So we think there's something inherent to the person that causes the output that we see. That would be EFA. If somehow the answers that we see somehow built up the overall score, maybe, that would be PCA. So I've seen PCA used in maybe eye tracking data or EEG data, where we're looking at the pattern of the data and we think that all together builds a picture of what the participant was doing. Generally in a scale development framework, which is kind of the way we're going to talk about EFA, people think that the underlying latent variable or psychological phenomenon is what causes the answers that you see on the scale. So another key difference between PCA and EFA is that only that shared variance is analyzed. So shared variance is analyzed. Unique variance is considered the leftover of that error. Okay? Whereas in PCA, all of the variance is considered important and is just parceled out differently. So a couple of different things to explain here terminology-wise is common invariance, which is where we have those overlapping variance between items. Sometimes that would be considered our systematic or our good variance. Unique variance, which is variance only, is it just not liking the word variance twice? Can I not spell? Okay, just doesn't like the word variance twice. I also cannot spell, but it's related only to that item, so it's the error variance. And I stole this picture from the Andy Field book, where communality is the variance that overlaps with other variance. So it's kind of like R squared for each item. So variable 1 here, which is completely subsumed by variable 3 and 2, has a communality of 1 because all of its variance is shared somehow with other variables. Variance of the variable 4 here, though, is mostly only unique variance, and so its communality is 0. And so in PCA, we're going to look at all of the variance, but in EFA, we're going to ignore this unique variance. It's going to be considered error. Now, when we're doing this, what we'll do is we'll create a correlation matrix, or the underlying math in the background. What's going to happen is it creates a correlation matrix, and that's your traditional correlation matrix that we've been doing all year. And then we're going to try to reproduce it. So a reproduced correlation matrix is like we build this model of all these different clusters of variance. So remember, I said the purpose of this design is to group variances together, or to group items together that appear to be measuring the same thing. And so we're going to reproduce that correlation matrix from our predictive model. And if we subtract those two things from each other, we get the residual matrix. The residual matrix is how far off our model is from matching the real data. And so a reproduced correlation matrix you can think about is like, this is how the data looks. and then we take the way the actual data looks, and our residual matrix is how off are we. It's very similar to the idea of residuals in regression, where we predict someone's score. So I think they're going to get 100 on this IQ test, and they get 105. I am 5 points off. That's a residual. So residual correlation matrix is the same idea. So we want these to be very small. The other, and arguably the most confusing thing about factor analysis and PCA is eigenvalues. So eigenvalues are sort of mathematical representation of variance. They don't really have a scale, and so it just sort of represents how much variance is accounted for by any group of items. So let's say you have a data set, and there sort of looks like there are 3 clusters of items. Eigenvalues will have numbers that represent how much variance is accounted for by each cluster. So it's kind of like little r-squareds, but they're not in a particular scale, so you can't interpret them as like 30% of the variance goes here, 10% of the variance goes there. They just are big if they are important. And we'll get to in a minute on how big is big. One of the most confusing things about that, though, is that when we're calculating eigenvalues, if you have a 20-item scale, I don't even know. If you have a 20-item scale, you will get 20 eigenvalues. And what happens is that it creates these clusters, but we still have to account for the unique variance that's left over after those clusters occur. And so we get as many eigenvalues as you do items. But you don't expect 20 clusters when you have only 20 questions. The whole point is to reduce the data. So we're instead going to only take the largest eigenvalues. Okay, so some questions that we could potentially answer with EFA is we can look at like how many underlying patterns, so how many factors are there, and how many of them best fit the data. And does that match an expected theory? Sometimes the answer is yes. Sometimes it's a hot mess, and the answer is no. We also could treat this from a scale development perspective, which is what I'm going to do because that's my specialty, is that we're building this new measure, and does that new measure match the theory? So do the questions do what I think they're supposed to do? So does question 1 actually measure, let's say of the big 5, let's say does it actually measure openness? And what are those underlying pieces? How are the questions grouping together? And what questions can we get rid of because they don't work the way we think they do? So I have a funny example from a study that we've been working on where a student had a question that said, how pretentious is blah, 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 blah. And freshmen don't know what the word pretentious means. So we had to eliminate that question because it just didn't work the way we wanted it to. Power here, incoming cat. Ugh. All right, so power in EFA, there's not necessarily a good way to calculate. So I can't open G-Power and say I have 10 questions, I need 400 participants. Anytime you're dealing with a model fit scenario like EFA and structural equation modeling, it's either going to fit or it's not. And so we want really large sample sizes so that no one person can unduly influence our model. Oh, cat fight. All right. So the videos either get interrupted by the UPS guy or by the animals. One of the two, can't win. All right, so we were talking about model fit. Okay, so we want really large sample sizes so no one person can unduly influence the model. And also large sample sizes allow us to meet the central limit theorem and kind of even out the picture of the data because there's lots of people and sort of normalizes in a sense. And so these analyses tend to need very big sample sizes, but the model is or is not. And so a lot of EFA is model tweaking, figuring out what is the best model, hence the exploratory part of the word, where a lot of structural equation models are more confirmatory. So I think this is the model. Let's see if it works on this group. Okay. Smaller sample sizes just make it hard to fit because any one person can screw that up. If you have very, very big data sets, so I've had the pleasure of working with some exceedingly large data sets for dealing with people anyway. Are you done down there? All right. Sometimes maybe you can split them in half and do half CFA or half exploratory factor analysis and half confirmatory factor analysis. Or you could have studies like when we've published where we ran 5 different versions of the scale until it finally worked out right. There are some rules of thumb, and I'm pulling this from a bunch of different books on EFA, but there's also a really great article, Preacher and McCallum's 2003 Tom Swift article, covers a lot of the things that we're going to talk about. And so one of the big rules of thumb is 10 to 15 participants per item. So if you have 10 items, you need at least 100 participants. You really cannot publish these things with less than 100 people. Now, if you have, let's say you're studying the states, clearly there's only 50 of those, but anything where you're dealing with participants where there are people less than 100 is not publishable. I know this because I have tried. And 300 is kind of the gold standard. All of these are estimates, and I always tell people to shoot for as big as they can, and if feasible, like balancing money and time and effort against model fit. All right, so some assumptions and some data screening here is the number of variables. So the more variables you have, the better. And this is about the only time you'll hear me say that, because generally more variables complicate models. But in this sort of design, what we're trying to do is reduce variables. And so it's hard to reduce 5 because you're already pretty small. And if you're building a scale, you have to have at least 3 items per factor or subscale, if you want to think about it that way. And so if you only have 5, that's all you got. So at least 10 variables are recommended. Some of them might be crap that you have to get rid of. And some of them may not work the way you want them to. So the more the merrier here. But keeping a nice balance of items to people. So you cannot have more items than people. That's another crucial issue to deal with. The types of variables we're going to be dealing with here are mostly interval and ratios. We want continuous data. You can run this on non-continuous data, specifically like kind of yes-no binary outcomes, using polychoric or tetrachoric correlations. But at that point, you should probably consider switching to item response theory. Item response theory has a very different focus than maybe an exploratory factor analysis. So you'd be kind of changing the way you're talking about your data, but it's more suitable for sort of yes-no outcomes. Okay, sample size we already talked about. The normal data screening applies, so accuracy, missing, and outliers. Additivity in the sense that we don't want correlations that are perfect. We want correlations that are high. That's sort of the point of these analyses, but perfectly correlated variables will throw an error message. Normal, linear, homogeneic, and homoscedastic. So your kind of traditional data screening, which if you want to learn more about, I have several videos on. Now, some things that happen like sort of at the start of EFA, after data screening, before the EFA part, is you have to kind of ask yourself, do I have a good data set for this? So there's ways to test for correlation adequacy. So are the correlations big enough to even do EFA? And there's Bartlett's test of correlation adequacy, and so significant values are considered good. However, this test is sensitive to sample size, so it pretty much is always significant. I don't think I've ever seen it where it's not, but it might be a good low-pass filter for you to determine if this will even run. I mean, it'll run, but it may not work if your correlations are very low. Next question is, do I have a large enough sample? So sampling adequacy. So do you have at least 100 participants? You can just kind of ask yourself. But you can also use the KMO statistic, or Kaiser-Meyer-Olkin, and you want high values close to 1, at least above 0.7. So I've heard a lot of rules about this thing. You just want bigger, better numbers. And so you'll get the sampling adequacy. So there's correlation adequacy, large enough correlations to run EFA, and sampling adequacy, enough sort of variance to also explore EFA. After I do that, so this is sort of getting started, one of the next big things that we're going to look at in the data is how many factors or how many components do I have? I'm going to focus here on EFA. So how many factors do I have? Well, there's sort of 4 different ways that you can ask this question. The first one is theory. You're going to have an idea of how many you might expect. Generally, if you know that you want 3 out of your scale, sometimes people might test 2, 3, and 4 to see which model fits best. And you hope that the 3 model fits best. So theory is going to be based on your design of the scale or someone else's previous work on the scale. Another thing we can use is called a scree plot. Scree plots are a visual depiction of those eigenvalues that we talked about. And so what you want to do is look for the scree. I actually looked this up recently on why is it called this. And so that's the like slope where if rocks are falling downhill, they'll like basically stop rolling. And essentially you want to look for the large drop off. So given this eigenvalue chart, so this is a representation of eigenvalues, and here's the 18 components in this example, is we want to look for the point at which essentially all of the dots start to line up in a little row. Sometimes this is called the point of inflection, where the dots stop having big drops and they start just like kind of leveling out. So there would be 4 factors, so 4 dots above the point of inflection. So this is kind of hard. It's going to sound like voodoo and the first couple times you do it. You're essentially looking for the largest drop-off point. So you could also have said 2 here, but it would be hard to ignore these other 2 little factors because of this second large drop-off. Hey, if you want less voodoo and more real numbers, you can do a parallel analysis. And that analysis tells me how many factors are greater than chance. And so what you do, and it's explaining the points here, explaining the picture that we'll look at in just a second, but what a parallel analysis does is it takes your data and runs the eigenvalues. And it takes your data and scrambles it all up and runs those eigenvalues again. And so we look at how many eigenvalues are greater than a randomized data set. So if your eigenvalues are not greater than a randomized data set, that implies that they're not really useful. So what we want to do is see the number of items that are greater than chance, and it creates a scree plot for you, part of the psych package here. The black line here is the Kaiser criterion, which we're going to get to in just a second. The red dotted line is the random data. The triangles are your actual eigenvalues. And so we're essentially looking here for where the blue lines and the red lines cross. And so it's really hard to read, and so what will happen is the R will like spit out a number for you as well. Okay. Now on this scree plot, I would say there's probably 2 factors, because the largest drop off is here, and it seems to level out over here. Maybe 3. Here, the red line, it seems to cross somewhere between 4 and 5. But like I said, once we look at this in R, it actually will give you the exact number. One last method for determining the number of factors to run is the Kaiser criterion. Oh, excuse me. Now with this, people are moving away from it slowly because the basis of it is the technical term of like meh. But it's an older rule of thumb, and I like to teach my students that just so that you know what the heck it is when you read people talking about it, or if you get a reviewer that asks you. It's not really well supported anymore, but the old rule was that you should look at eigenvalues that were greater than 1, because the assumption was if the eigenvalue was greater than 1, it was important. Or the newer literature argues for 0.7. And I've found that this tends to overestimate the number of components that I actually end up deciding on. So it tends to estimate more components or factors than you might actually need. Once you figure out the number of factors to run, the next thing you're going to do is strive for simple structure. So simple structure is this like final solution, and it's the simplest solution. So this is the keep it simple, stupid principle. And so the first question is, how do I achieve simple structure? Okay, so this part is usually where most like traditional ANOVA people run screaming from the room, because it's like, well, this sounds like magic. What happens is we're going to take our data. So what we're creating are these factors where we're saying that these 4 items cluster together and these 4 items cluster together. But what actually happens in the background is some regression that creates sort of a picture of what someone might score if all of these items clustered together. Okay? And so what we can do is rotate those sort of regressions to create the best fitting model where we have the smallest residuals. So we started this lecture by talking about the real correlation matrix and the reproduced correlation matrix, and we want the closest we can get for them, where the subtraction of them is the smallest number possible. Rotation creates those small numbers. And what it does is it creates small numbers by maximizing the values on one factor, minimizing the values on another, which is what you want. Okay. There's two types of rotations, and within those there's like lots of different types of those rotations. So there are oblique rotations and orthogonal rotations. So oblique rotations, oblimin is easily the most popular, and this is when we allow our factors to be correlated when they're being rotated. An orthogonal rotation, where Variance is definitely the most popular, forces those factors to be uncorrelated. Okay. So let's skip this fitting estimation thing and talk about what the heck you mean by correlation. Okay. So imagine here, also stolen from Andy Field, here we have factor 1 and factor 2, and all of these dots are the items. So we can see that there are two clusters here of items that go together. If the rotation is orthogonal, it forces those two factors to be uncorrelated, which means that they have to rotate at 90-degree angles. You can have more than two factors here, it just makes it too hard to draw. So when you're forcing them to rotate at 90-degree angles, you're going to miss a lot of these dots. So we want our lines to be very close to all of these dots, just like in a regression. What we can do instead is do an oblique rotation, where the lines are allowed to rotate, or the factors are allowed to be correlated, so they don't have to rotate at 90-degree angles. So the angle can be different for each one, and then we can hit those dots better. And so an oblique rotation is a much better representation of our data. That's why it's in bold and orthogonal is not. And this is another question I love to ask on quizzes. Why would you ever do an orthogonal rotation? The answer is you shouldn't, because in psych, at least, things are rarely ever uncorrelated. And so why would we force them to be uncorrelated? That seems like an unnecessary assumption to say that our factors are uncorrelated. Additionally, why are things on the same scale if they're uncorrelated? So I've never understood the idea of an orthogonal rotation. I also had a really fantastic teacher that explained this to us, where if you have items on the same scale, you kind of expect them to be correlated, otherwise why would they be on the same scale? So then forcing them to be uncorrelated seems odd. Additionally, if those factors are truly uncorrelated for some magical unicorn world, a oblique rotation will allow them to be uncorrelated. So there's not a reason really to use an orthogonal rotation unless there's some strong theory argument, because an oblique rotation will allow them to be uncorrelated if they are. And so if you want to answer this question, what you can say is that oblique rotations, if they're truly uncorrelated, will give you the same answer as an orthogonal rotation. And the assumption of uncorrelated factors, at least in psych, is untenable at best. Right? So that means that it's usually not a good idea. Okay, so how do I do that mathematically? Well, we're going to tell it to run an oblique rotation, but there's also some different types of math that go on here. So all semester we've been working with, unless you've done log regression, we've been working with least squares. So ANOVA, MANOVA, ANCOVA, regression, everything up to this point has been least squares math. Okay? So we're going to switch here and we're going to use maximum likelihood. So maximum likelihood is the most common one that you'll see. It's usually also the most common structural equation model. And what it does is it looks for the maximum likelihood answer, essentially. So it's an iterative process that picks the most likely solution. For principal components analysis, principal components math is the most common. Okay. And principal axis factoring is sort of like halfway in between the two. Okay. So we've talked about how do I set up simple structure. Now the question is, how do I know that I've achieved simple structure? Well, what we'll do is we'll look at a loading table. A loading table is where the correlation between that factor and its item. So for item 1, how related is it to factor 1? Okay. And so we want variables that load, so that's the term that people use here, on one and only one factor. Loading here is a correlation of 0.3. And 0.3 is a super common criterion. Remember, that's a medium effect size where at least approximately 10% of the variance is related. And so we've just kind of picked this point as sort of the lowest that we expect items to be related to their factor. You can go higher, but people don't tend to go lower. So the simple part of this is that we want them to load on one and only one. So that's where the name simple solution comes from. And we'll actually eliminate questions that split loadings, where they load on multiple factors, or don't load, where they don't load on any particular factor. And we would consider those bad items, because we kind of want them to be on one and only one. And one reason that you might not want a question to load on multiple factors is, let's say you're creating a subscale. Well, if one question is in both subscales, you're using that question twice. And so it kind of is a little weird for it to be in both subscales. Another thing you have to be concerned with is that factors or components need to have at least 3 items, or you've overfactored, meaning that there are too many factors and you should take one out. And this is an iterative process. So if items are bad because they split load or they don't load or whatever, you will run this again. So you'll take them out and run it again. Once you get to simple structure, where there's each item loads on one and only one factor, and this might not ever be achieved. It might, just the whole model might barf, or it may never work. You know, you may eliminate items and then you're left with nothing. Okay, I've had that happen. But let's say you do end up with simple structure. Then you would want to test the adequacy of the model. Essentially, how good is your model? Okay. And that's kind of similar to checking maybe a p-value or an effect size. But instead we're going to use fit indices. Broadly, fit indices fall into 2 categories. Goodness of fit statistics, where we want large values that are close to 1, that imply the correlation matrix, the reproduced and original correlation matrix match. Or residual statistics, where we want numbers that are very small because it's how much they mismatch. There is a literal alphabet soup of these, so I'm just going to tell you the most popular ones. So for goodness of fit statistics, the 2 most popular ones are the NNFI or the TLI. Those are actually the same thing. Just depends on which program you're looking at, which letters they're going to give you. And the comparative fit index or CFI. They are excellent at 0.95, acceptable at 0.9, and poor at less than 0.9. So we want a really strong match between the original and reproduced correlation matrix. That is from the Hugh and Bentler article. Also from that is the 2 residual fit statistics that are the most popular, which is the RMC, standardized root mean error of approximation, and RMSR, root mean square of the residual. Sometimes programs will tell you SRMR, which is the standardized root mean residual. It's a very similar statistic. They're excellent at less than 0.06, acceptable between 0.06 and 0.08, and poor at 0.10. Don't ask me what happens when you get something that's at 0.9. I've always wondered that myself. I always slap that into the acceptable category. These are guidelines. I have published RMC values of 0.12, but we've talked about how the model should maybe be considered tentative. So you will report several of these, so you don't want to cherry pick only the good ones. And these are the big 4 that I always try to report. There are more of them. If you are interested, especially if you're going to look at structural equation modeling, there's a bunch of books that cover just all a bazillion of these. Another thing we can do to test the adequacy of our model is look at the reliability. So reliability is kind of like how much do these items hang together. Cronbach's alpha is the most common. 0.7, 0.8 is acceptable. Another thing that I can look at is theory. Do the item loadings even make any sense? can I tell you what this factor is? So by looking at the questions that hang out together, can we label them? So think about this as cliques in high school. So you figured out each person can only go in one clique. You can't be in both, right? So you can't be in the band nerd category and, I don't know, the cheerleaders. I'm just making this up. So you can only be in one group for simple structure. And then can I give you those labels? So do the items make enough sense together to get a label out of? Okay. So what we'll do now is we'll walk through an example of that using self-determination theory and work on running a complete exploratory factor analysis. So let's now get into the complete example of an EFA. A lot of people are interested in self-determination theory, where motivation is determined by intrinsic, maybe extrinsic factors. So the scale was developed that assesses why people are in college. And we're going to test if those questions fit some sort of factor structure. And those questions are available online through this EFA scale document. And what it is a 32-item questionnaire that, okay, computer, neat, there we go, has a lot of questions like I wonder what I'm doing, find it boring. So the starred ones are reverse coded because I need a degree to show myself I can succeed, etc. So we're going to flip back and forth between this and R, and we're going to start with our data screening like we normally do. But if we want to think about power in the sense of do we have a large enough sample size, before we get to sampling adequacy, let's just even see. So my data set has 206 people in it. I can also see that here in the environment window. 206 people is enough. There are a lot of items, so we don't meet that 10 per item rule, but we should have enough. Okay, so let's check our min and max scores by using a summary of the data set. My computer is not going to play along. Okay. So I can already see I have a couple of missing data points. Good grief, computer. But everything appears to be scaled 1 to 7, which would fit into my accuracy check. I also don't have any extra columns that I don't need. The other thing I would want to do is reverse score those items. So that second question here, why are you in college? Because I experience pleasure. A high score would be a high answer on this. I strongly agree. But a high score on this, I wonder what I'm doing in college, would actually be a negative. So we want to switch those. Right. So the rule actually is, if I want to be perfectly accurate, minimum. All right. The rule on switching things is to use a little formula called min plus max minus participant score. So in our example, 7 plus 1 minus the score. So if a person scored a 7, that would be 8 minus 7, so they get a 1. If they scored a 4, that'd be 8 minus 4, so they get a 4, etc. So on that scale document, we can see that 6, 9, 17, and 27 are reverse coded. So let's actually reverse them. One thing I always do, because I can screw things up, is make a table of just one of the questions beforehand and make sure that I've done it correctly. So if I run a table of question 6, I can just see the distribution of the data, which is heavily biased towards 1. Then I can do my reverse coding by taking the data set with all of the columns that I'm interested in. So here are all the item numbers that need to be reversed. Fill in my little formula. So 7 plus 1, so 8, minus all of those columns again. And this will overwrite the original columns, but relearning the data step is only a couple lines away in case I screw this up. I run that table again, and now I can see that all it's done is taken everything and flipped it, which is exactly what I wanted it to do. So we've been able to reverse code the data set with just one line of code, which is a little faster than some of the recode functions in maybe the car library. All right, we do have a missing data set, and we have a lot of columns. So this is one of our examples where we're going to get to use mice. And so EFA is usually a great place to import missing data, just because we tend to have enough information and enough columns to actually make this work. So we're going to create a missing function that just calculates the percent of missing data in a particular row or column. And then we're going to use apply on the entire data set across rows, so one for rows, remember, and apply, and use our new percent missing function just to create a missing score for each person. If I run a table of that, I can see I have 8 people who are missing 3% of their data, which is where we can fill in, and 1 person who's missing 28% of the data, so we're going to exclude them. So I'm going to make my replace people data set, where I'm going to subset out the people who are missing too much data. Now I'm going to look at this new replace people data set and make sure that my columns aren't missing too much information. So 2 for columns here. And on that one, I'm not going to save it. I'm just going to look at it because I have way less columns than people. Remember, this is already a percentage. So these are all less than 5%. Remember that this is not proportion. So this is less than 1%, and this is less than 0.5%. Okay. And then we're going to use the mice library, to replace that data. So remember, the way the mice library works is that we're going to create a temporary data set where it's going to multiple impute data points, and then we're going to fill in those missing data points. Remember, this number here can be from anything from 1 to 5 because mice auto creates 5 different randomized data sets. I just always pick 1. You can pick 4 if you want, or you can set it up to randomly pick for you. Right, so it's imputed my missing data points, so I can actually see which columns were missing at least 1 data point. I'm going to create my no missing data set, and now if I do a summary of that, the nice thing about mice, remember, is that it looks at the type of data that you have and estimates data that fits within that type of range and a value. So as long as if they're whole numbers, it will estimate whole numbers for you. Now let's create outliers. So we have 32 different columns to pick, and that's going to end up being our degrees of freedom for our Mahalanobis score. So for Mahalanobis, we want to use the name of the data set all 3 times here, and there are no columns to exclude in this example. Our cutoff score is going to be based on chi-square, because remember, our Mahalanobis scores are chi-square distributed based on the number of the degrees of freedom here is the number of columns entered, not the number of people. Right, so let's go back. So our cutoff score, 1 minus the big important rule, based on degrees of freedom of the number of columns in our data set. We're going to calculate Mahalanobis. And I dropped the missing functions because I knew I didn't have any missing data. Our degrees of freedom are 32, which is what I was just talking about. That makes our cutoff score 62.49. And we're going to find a summary of the number of people whose scores exceed the cutoff score. So a false here means that they're an outlier, because, I'm sorry, I said that a little backwards, but Mahalanobis less than the cutoff. So the true people are people whose scores are less than the cutoff. False are people whose scores are above the cutoff. And for this example, we're going to exclude people whose scores are greater than the cutoff. So we're getting rid of 11 outliers. Now this is miced, and so your number might be slightly different than mine. It just kind of depends on if the person is right on the line or not, because we will get slightly different answers of our mice. Not for the cutoff score, but let's try again. But I got 11 again. And so generally if that happens, that means that someone was very close to the line. And I would try running this with and without outliers to see what kind of differences I get. All right, so now I've excluded my 11 people, and I'm going to check and make sure that I don't have any problems with additivity. So look, in this example, I had 12 from before. We want these items to be correlated because that's the point of VFA, but we're just trying to make sure that nothing is correlated at 1, because then it won't run. And we're going to use our symbols for numbers chart to look for that. And so you're going to get a lot of symbols, hopefully, because that means they're all correlated to each other. And mainly we just want to make sure that anything on the off diagonal, so these ones are supposed to be there. That's it correlated with itself. And we're really looking for things on the not diagonal that are a 1. And this will break up into 2 parts. You can also play with the window size if you really want it to be one giant window. I don't know if I can totally make this fit. You can also dump this into Excel if that helps. Okay. You can look at the correlation numbers, but I find this table very hard to read. Right? I like the symbols for numbers table. Squish this over here. All right, since this is a normal analysis, I want to check it for my assumptions of a parametric test. So it's a parametric analysis is what I was trying to say. And we're going to test the rest of those assumptions with a fake regression. So even though EFA is regression on steroids, we still have to analyze for our assumptions using that fake analysis. So we're going to create a random data set. Remember the 7 here is just my lucky number. It's actually not my lucky number, but it's the lucky number for this particular analysis. It's not base, it's anything above 2 to make that run. So you can try a different number than me. This creates our random predicted scores. We're going to pull our standardized residuals or studentized residuals from the analysis, and since they're standardized, that gives us an easy metric scale to look at. And we're going to scale our fitted values as well, so that everything we're going to look for in these next analyses will be centered around 0. That's just the setup. Now let's look at our normal histogram. Remember, we have mice and we are using a random thing, so we're all going to get slightly different things, but hopefully everybody has this nice, beautiful histogram where it's centered over 0 and in between 2 and 2. So this, I would argue, looks pretty normal. For linearity, we want to again look and see that dots are mostly on the line between 2 and 2, and I would say this one looks pretty good. For homogeneity and homoscedasticity all at once, I want the dots to be centered around 0 for homogeneity, and that's okay this way, not so much this way. 2 to 4 is not a good spread on the side, so maybe slightly heterogenic. Also, we want the dots to make a random smattering. Even if I'm real nice to this graph, it's starting to be heteroscedastic, so it's starting to spread. The spread here is smaller than the spread over here. So kind of iffy on those two. The next thing we want to do is start with our EFA. So even if you rerun this, it's still a little messy on homogeneity and homoscedasticity. Okay. So do I have a good data set for EFA? Well, I have at least 32 questions, so that's good. I have at least interval scale, depending on how you feel about Likert scales. And I have 194 in the example I'm doing right now. It's at least 100, but it's not really quite 10 for each item. So we should look at correlation accuracy, adequacy, and sampling adequacy. So we're going to load the Psych and GPA rotation libraries. I think Psych might load GPA rotation, but I've always found that it works better if I just go ahead and load it. Okay, it's probably a placebo. But the way that you run Bartlett's test is this core test.bartlett. And I've got my correlations from earlier that I'm going to dump in here. But if you haven't run correlations, boo on you, go back and do additivity. But you can create a correlation table to put here. N equals the number of rows in your data set. So for this one, I find that it's a significant effect, which means that my correlations are large enough to continue. The way that we're going to check for sampling adequacy is to use the KMO function on the correlations that we ran earlier. And what we want to see is the overall mean sampling adequacy is at least 0.7. So the sampling adequacy is pretty good for all of these. It's all above 0.8. And then just like a global average is 0.92. So that implies that our sample and our correlations are probably large enough to run EFA. Let's jump into the sort of 3 big steps for EFA. How many factors should I have? Well, the theory behind the scale argues that I should have 3. And then now let's check some of our other non-theory based options. So what I'm going to do is run fa.parallel. So fa.parallel runs a parallel analysis. I'm going to save it. You run that on your data set. FM for factor math equals ML for maximum likelihood. FA for factor analysis equals FA, give me factor analysis. You can also type in PCA or both. Now, even though I'm going to save this, it's going to go ahead and spit out a bunch of stuff for me. So let's look at that parallel analysis scree plot. And what this suggests, so this is the one we looked at earlier, is that it's somewhere, this is the largest drop. I'd say probably 2 factors, maybe 3. I'm kind of leaning just towards 2. But if I look over here in this window, it actually spits out and tells me that there's 5. And so this is the point at which the red line crosses the blue line. And so the parallel analysis suggests 5. I would say my scree plot probably suggests 2. And then now we can look at the Kaiser criterion. So the reason we saved this was that we could sum up the number of eigenvalues that are over 1 for the old criterion. That's going to suggest 3 factors for me. And we can sum up the number of eigenvalues over 0.7. That's also going to suggest 3. So I've got 2, 3, 3, and 7. Or 5. Sorry. So on that scree plot, I might disagree. That might be 2. I think I see 3 because I know there's supposed to be 3 there. But 3 is kind of a common number. So we're going to try 3. And we could try all of these if we wanted to see which one fit best. So now we're actually going to run that factor analysis, and we're going to use FA for factor analysis. The arguments are the data set name, the number of factors. So this is where we'll put 3. Rotate equals, and then we'll put in oblimin. FM is ML for factor math, just like before. You don't have to save it, but we're going to save it so that we can use it later. So for round 1 here, I've got my dataset name, 3 factors, oblimin, rotation, and maximum likelihood data. I'm going to print all this out. I'll make it a little bigger here. And right now, the only thing we're really interested in is this giant standardized loading pattern matrix. I'm going to highlight all of this and actually use Excel. There's probably a good way to do this in R, but I found that most people like it in Excel because of the nice highlighting that we're going to be able to do. Okay, now my computer is taking a nap. I'm with you, computer. I'm gonna hit Control V or Command V to paste that. Okay, now watch this. What we're gonna do is click Data, Text to Columns, and you can actually just hit Finish. So what that does is it puts all of the different columns into their separate Excel sheets, which makes this really easy to work with. H2 out here is communality, that's like R squared. U2 is the opposites, uniqueness, so this whole thing adds up to 1 all the way across. Complexity is the item complexity. Don't care. So those are useful, but not what we're looking for right now. ML1, ML3, ML2, those are your different factors. The numbering and names here don't matter so much right now. So I'm going to highlight all 3 of these, click on Home, go over here to Conditional Formatting. Under Highlight Cell Rules, pick greater than. I'm going to do 0.299. So this is going to highlight everything that's greater than 0.3. And what that does for me is it makes it a nice visual way to see where items load. You can also do Conditional Formatting, Highlight Cell Rules, less than, negative 0.299. This will capture any of those negatives. Kind of depends on how you feel about negatives. Sometimes people delete negatives because they don't want it to be related in the opposite direction to the factor. And now what I can do is make sure that each column has 1 and only 1. So I can tell right away that question 4 is bad because it has 2 loadings. that's what we were calling a split loading earlier. Question 15 is also bad. Okay. And those appear to be the only two. This will just allow me to see kind of visually all the items that are bad. If you're working with a crap ton of items, you can also click Data and Filter. You can actually filter, click a little down arrow here, choose one, by color, and then pick the red. And this will allow you to see all the items that load on item 1, and I can already tell they're too bad. You do that for all 3 of them. So when I'm working with like 100 items, I might do that, just so I don't miss any. All right, so we've got 4 and 16 that are poor. So what I'm gonna do here, was it 16 or 15? 15, sorry. Is I'm gonna rerun that analysis, exact same one, and now you'll see that I've subtracted 4 and 15. You just wanna make sure your column numbers and your item numbers line up, because if you had like a subject number or something else to exclude, so these numbers only match because my items and columns are the same. Essentially, you want to exclude question 4 and question 15, which just happen to be column 4 and column 15 in this example. We're going to run that whole thing again, and now look at our loadings. So you notice I ignored all the rest of it, all the fit indices, all that other stuff. I'm gonna come down here, I'm gonna paste. Sometimes in Excel we'll get lucky and it will automatically figure it out, but I'm gonna click text to columns again and finish, but the highlighting did stick. So now I wanna make sure that each one is on 1 and only 1. And so all of these look good. Okay. We would also exclude items if they didn't have any highlighted questions. So now that we have our final model, what can we do with it? So that is where we've achieved simple structure. And then I kind of go through this, and this is where I talk about Excel. That's why this particular cheat sheet's so long. Now we want to look at the things in the final model, only the final model. And so what this tells me is the variance accounted for by each item and the factor correlations. So I can see that these items are correlated, so oblim was a good choice. Our second and third factor have a pretty strong relationship at 0.49. Now let's look at fin indices. The root mean square of the residuals was 0.05, and that's pretty good. And where you find that is somewhere here in the middle. Root mean square of the residuals, RMSR. We're also going to look for RMC, or root mean squared error of approximation, 0.096. So that's in the acceptable range. And that confidence interval is completely in the acceptable range, so that's good, 0.084 to 0.098. Another thing we're going to look for, oh, look at this. They've actually changed the output since I made these slides, right? This gives you multiple R squared and correlations. So that's new. This is the part I was talking about a minute ago. Okay. I got sidetracked there. Let's look at Tucker-Lewis. Tucker-Lewis is 0.82, so that's not very good. You'll notice that mine in here is just slightly different, and that is due to outliers and mice. Okay, but it's close. And then the last one we really want is CFI. CFI is one of the most commonly reported ones, along with RMC, so you gotta suffer through calculating it. And the way you calculate it is 1 minus, and then this whole thing, chi-square for your model minus degrees of freedom for your model, divided by the null for chi-square model minus degrees of freedom for the null. Now, those are all hidden away in the background because we saved it. Additionally, they're all kind of reported in here somewhere, but I find it very confusing, so I just wrote a little function to pull those numbers. And be sure when you're copying this, you keep the open and close parentheses in the right place, or it will do the wrong thing. Okay. You can tell if you're close, it will always be just slightly above TLI. So let's go over here. I saved this whole thing as final model just so that I could keep using my math formula here of chi-square for my model minus degrees of freedom for my model divided by chi-square for a null model minus degrees of freedom for a null model. I got 0.86 essentially. TLI was 0.82, so I'm doing pretty good. And are the fit indices okay? Well, no, not really for TLI or CFI. For RMSR, they're excellent, and for RIMC, it's acceptable. So I got a mixed bag here. Got half and half. And I would present it as such. Achieving simple structure is always a good thing as well. So let's add to the fit indices, give people multiple indicators of evidence here, and add reliability. So something that I think is in some of my new videos, but I just want to repeat, is that the psych package has a cool alpha function. We've already got psych loaded. But 90% of the time, some of the things that we're doing involve ggplot too. ggplot is a fantastic package, but sometimes it takes over the universe and it has like evil Pinky in the Brain type plans. And so it also has an alpha function. And the alpha function has something to do with color. So what you want to do is make sure that when you're running psych alpha, you just put psych : in front of it. That will save you a lot of headache and teeth gnashing when it gives you an error message about color that makes no freaking sense. So this just tells it, be sure you're using alpha from psych and not from ggplot. And we don't currently have that open, but every once in a while it will, I forget what it is exactly that makes it open. I don't know if it's this plot or what. Let's click over here in packages. It shouldn't be open right now. I have not used it, but see that it is. So just a way to save yourself some hassle and some tears. Okay. So first I'm going to do is save each factor as a separate set of concatenated numbers. And these are the column numbers that associate to where the factor loaded. So coming back over here, what I've done is looked at my final model and picked question 1, question 3, question 7, 8. So if they're highlighted here, I stuck them in a little concatenate over here. If I do the same for factor 2 and for factor 3. I'm doing okay because factor 3 has at least 4 items. So I need at least 3 really. And what this does is it allows me to use those numbers instead of typing them all out in this function. So I'm going to save those. Now, in reality, this is just just a vector of numbers. But I can take that vector of numbers and stick it in the second comma here, which means give me all of these columns. So when you do this, if your columns are all off by one number, you have to add 1. And that might make you sad. But I always leave a little note for myself, like, wait, why the hell did I add 1 here? And I have to remind myself, hey, there's a subject number at the front or something. But what that does is it allows me to use these little factor lists over and over again. Okay. So I'm going to run the alpha function on the data set, just the columns I'm interested in, not the entire thing, because we want reliability for each subscale. And it gives you a whole bunch of stuff, like so much stuff. So what I'm really looking for here is raw alpha. Raw alpha is 0.95. I'm doing great. Okay. If it's not so good, I could look at each individual question and see what alpha would be without that question. Okay, so what this is the alpha if question 1 is dropped. So you wanted the number to stay high. So our alpha is 0.95, which is really good. For factor 2, our alpha is 0.86, also good. For factor 3, our alpha is 0.9, which is a little surprising because small scales with small alpha, small numbers of items, sometimes it's hard. So that's also good. So all 3 of our factors have great reliability. And they tend to have pretty good reliability when their correlations are pretty high. In addition, if they are loading strongly on their factor. All right. So the last part of is my model adequate, right? So we looked at fit indices, we looked at reliability. Now, do those questions match some kind of theory? What the heck do these items even mean? I find this is the part that students have the hardest part with because we're not generally making our own scales. I feel like if it was your own scale, it would be easier. But you're looking at how these items load together. So this is why I've kept this file open. So let's look over here. I've got question 1, 3, 6, 7, 10, 11, 12. Let's look here. Question 1, pleasure and satisfaction while learning new things. Question 3, I can succeed. I've already forgotten what numbers. 10, 11, 12. College makes me feel important. Allows me to learn things I want to learn because it allows me to continue to learn. So lots of questions about learning and happiness. So we called that intrinsic motivation, or sort of a love of learning. Factor 2 appears to tag items that are all about jobs, skills, goals. So we call this one career goals. Factor 3 appears to be all of our reverse coded items, which is never a good sign. But boring, waste of time, don't know what I'm doing. So we call this one doubts. You should always be concerned when all of the negative items load together, because that implies that they're doing something different than the rest of them. If that's what you want, okay. If that's not what you want, not a good sign. Okay. So I've presented a picture of the model that starts with simple structure and then explains if this simple structure is adequate. Because you can have simple structure and it be a crappy model. It doesn't always happen, but it can. And so you don't really get a good model fit if you don't have simple structure. So we can do one or the other. It's kind of like reliability and validity. So we want to present a picture to people of the model. So what are the fit indices? What are the theory questions? What are the reliabilities? And so that allows people to make up their own mind if they like the scale. Right? Now the other thing I can do is create factor scores for each person, and generally this is useful, like what's people's average intrinsic motivation? Or can I use that intrinsic motivation to predict something else? So this is kind of like moving on into next steps. And so what we'll do is we'll save each factor score by creating a new column in each data set. So I've done dataset $, this is a new column name. I'm going to use the apply function again on just factor 1's columns. One for each person, and create an average score. I could do a sum as well. There's another function called row sums and row means. The thing I don't like about row sums and row means is that we'll just kind of like, oh, missing values, whatever, la la la. And I would like to know if there are missing values, like I don't want a total and to think that total includes all the columns. Whereas if I use apply and there are missing values, it shows me NA. So that's one reason I'm not showing you row means or row sums. But I think there's a way to turn that off, but I also like apply. It took me a long time to learn it, so I'm kind of stuck with it now. All right, so one for rows here. Now if I want to know factor 1's average, I can do that here in a minute. So I'm going to create 3 new columns in our no-out data set that are the average scores for each subscale. So I could call them their names as well. But these are the scores for each participant on their individual subscales here. If we run the summary function, we can get the mean of all of those. So 5 points intrinsic average, 6 points for career. So clearly career is a little more important than the love of learning here. And then pretty high doubts about school as well. So we can see where kind of people are landing. This is very skewed. All right, think about this for a second. It's a 7-point scale. I can also create the standard deviation for each one so I can see how much variance these have, and they're about a point each, which is not too surprising on a 1 to 7 scale. Okay. Also, here's an example of a write-up. So it just explains and walks through talking about each little different piece. And so I kind of have this broken down into before you start, so data screening and sampling and correlation adequacy, to simple solutions and model adequacy, to understanding what the model means. And that just, to me, makes sense working through each piece of the analysis one step at a time so people can see how and when I made my decisions. I also created a table in Excel and sort of played with the sorting. This is a common way to report these, where the items are sorted by numeric question order, but kind of grouped by factor. Right? So all that together is a description of what EFA is, running the analysis, and reporting it.